Good afternoon, this is Schweitzer, and we're looking to get that out of there. Okay. A little video on what we call stoichiometry, math of chemistry, and we're looking to look at more involving particles, and can we do about particles? So something simple might be that we could look at is, okay, how many particles are in atoms are in these guys? So for example, this guy, you could write a chemical reaction if you want. Which would be something like water breaks into two H's and one O. So that being said, we get a grand total of 3 particles. You can see there's 1, 2, 3. So the work we would show here, and you could probably do this in your head, but we're really looking to focus on our work. There are 3 molecules, and get rid of molecules, and go to atoms. 1 mole, 3 atoms, and the answer would be 99 molecules, or atoms at this point. Okay, 127 molecules. Okay, how many atoms? Alright, well we got 6 plus 6 is 12, 24 atoms in this thing. So we have 127 molecules. Get rid of molecules and go to atoms, and it's going to be a 1 to 27 ratio. Here, again, you can multiply out to get your answer. We have 5 particles, so 223 at a 1 to 5 ratio gives you a number of atoms here. Alright, so what about this? What if we had 25 molecules of O2? How much water could we make? How much O2? So in this case, you'd see that you need 1 molecule of oxygen to make 1 water molecule. So 25 O2s, get rid of the O2 and go to the H2O. Now this is a little more complicated because I have 2 O2s. Okay, so in this case, one of these guys could make 2 of those, because there's 1 in each. So 1 O2 can make 2 waters. 2 oxygens here, 2 oxygens here. Now, notice they're equivalent in oxygens. 25 times 2 is 50 water molecules. And that should make sense. 1 water molecule requires 1 oxygen. I have 50 oxygen, so I get 50 waters. Alright, in this case I have nitrogen. Here's my formula. 250 nitrogens. For every 1 nitrogen, I can make 1 HNO3. 250 HNO3s. 1,000 carbon atoms. Okay, how many of these can I make? Alright, well let's show the work here. It's a 6 to 1 ratio. 1,000 carbon atoms. For every 6 carbons, I make 1 C6H12O6. 1,000 divided by 6. 1,000 divided by 6 equals 166. So we'd have 166, and it's a decimal version. We have some left over, but not enough to make a whole other one, so about 166 molecules of that substance. So here we go. Alright, so another question. We have 5. We're kind of moving in the same direction, but we have this number of molecules of heptane, the basic component of gasoline, which burns completely in excess oxygen. So we have some heptane here. So a couple things here. What do the coefficients mean in these problems? Okay, I got 1 here, I got 11 here, I got this and this. I often refer to this as the rate used. The rate used, so this is a rate that you're consuming it. The ratio, for one of these, I consume 11 of these, is the rate used. And these guys here are the rate produced. So, assuming you have none of this to begin with, you should end up with more oxygen, more water than carbon dioxide. particle-wise. That's another really important thing here, is that these ratios, this is called your stoichiometric ratio. Stoichiometric ratio. It's the 1 to 11 to 7 to 8 ratio. That just means that for every 7 of these, I get 8 of these. So if I got 70 carbon dioxides produced, I'm also going to get 80 waters produced. If I had 700 carbon dioxides produced, I get 800 waters produced. Not a terribly complicated idea. If I got 800 waters produced, all right, how many of these did I consume? And that would be 100. Okay, so 1, 11, 7, 8. This little thing might be the first time you've seen this. It's called an ice table. How do I set it up? So it's just a data table. It really is just a data table that I use to store information in. So it says I got this number of molecules of heptane, which is 5.023 e to the 1, 2, 3, 4, 5, 6, 7, 8, e to the 8th. So 5.023 e to the 8th. I don't know how much of this is impossible spots to put information. I don't know how much of this I have. It's saying excess. So there's, like in the air, there's lots of it. And I have 0 of this and 0 of this before I start. Okay. I'm going to run this thing until I lose all of this stuff. 5.023 e to the 8th. And I'm going to lose, okay, some of this as well. The question is a couple things. How much of this am I going to use? How much of this am I going to get? Okay, another name for use might be need. How much do I need? Okay, so let's do that math below here. Now, whenever I draw an arrow like this is a pretty important idea. When I draw an arrow like that, that means I am using the stoich ratio. So for every one of these guys I have, I need one of the 11 of these. Now, I use the word need. Anytime you're solving for a reactant, I often refer to it as a need. So let's do the math here. I have 5.023 e to the 8th, and for every 1 C7H16 I need 11 O2s. And you can go ahead and punch this in. 5.023 times 11.023 times 11 should be pretty easy mental math. 55.25. So we got 55.25 e to the 8th. I just multiplied this times that and kept this the same. Okay, that is now this guy. 55.25 e to the 8th. Now, how much of this do I need? Do I get? Whenever I solve for a product, it is a situation of getting. Okay. Now this guy would be down to 0, and this guy would just be, since I don't know how much I started with, I don't really know how much I'm going to end with. Okay. Normally I could subtract these two values here to get how much is left over, but I can't do that in this case. So now, how much of this am I going to get? Okay, and how much of this? I'm going to base this off of my limiting reactant, okay, which is basically off of this guy. If I consume, so I just use a term here called limiting reactant. We'll talk about that more in a moment. Limiting reactant. Okay, a little sloppy there, sorry. That means that this is the determining factor. For every one of these I consume, how many of these am I going to get? So based off this chemical, how much of this do I get? Okay, so let's do that here. I'm going to go 5.023 e to the 8th at a 1 to 7 ratio, and there you go. Now again, the stoichiometric ratio really connects everything together. This whole reaction happens in what I call concert. which is probably a term that you'd use differently. But if you think about it, what is a concert? What is that? A band concert. It's where everything happens at once. And in this situation, that's kind of how this is working. So 35.16. So it's 35.16 or 16. All right. 16e to the 8th. Now that would be CO2s. And that's produced or getting. Okay, so now I have this guy. You note that these two also interrelate. For every 7 of these, I get 8 of these. I could say for every 1 of these, I get 8 of these. However you want to relate this, it's all connected. It happens in concert. Everything happens at once. I can't get 7 of these without getting 8 of these. So I'm going to jump from here to here. I showed that one already, so let's do this one. 35.16e to the 8th at a 7 to 8 ratio. Now again, I'm using my coefficients here. This is the CO2, because this is CO2. This is H2O. And my answer is going to be the H2Os. All right, let's plug it in here. 35.16 times 8 divided by 7. And a little bit more, but not a lot, 40.18. Okay, so that's going to be 40.18. And this is e to the 8th still. All right, so what is the important takeaways here? The ice table is huge. Stoic ratios are huge. This is a really huge page here as far as lots of information here. How to use the Stoic ratio. Here's another example. Okay. All right, we have a table. Take a moment, pause the video. You got your own amount here now of copper atoms. Pause it and try it out. Okay. I want to figure out how much of each item I'm going to get. Okay. Solve for need and produced. Okay. So hopefully you can pause it and try your own. But we got 25, 3, 2, 5, 0. Don't know how much I have. It's in excess. So it's going to be that. Sometimes we'll use it this way. I'm going to lose x of this. I'm going to lose 2x of that. I'm going to gain x of this. I'm going to gain 2x of that. And it turns out x is just this. This is going to run out. X equals to 0. So x equals 25, 3, 2, 5, 0. Now you notice that this is just a 1, a 2, a 1, and a 2. That's a 1, a 2, and a 1, and a 2. That's just the Stoic ratio. You can choose to think of it like that. Eventually we use that more commonly, but let's just put our numbers in here. Okay, so at this point, let's just try that. All right, let's try a different color here. So this is going to be minus 25, 3, 2, 5, 0. Minus, I'm going to double that up now, so I'm going to show my work here just so you can see. 25, 3, 2, 5, 0. Get rid of the 1 copper. That's this one is this one right here. And going to, I'm jumping to here, so it's 2 AgNO3s. So I'm doubling that, and it's solving for a reactant, so it's a need. 506,500. Okay, 506,500. And yep, and that is going to be how much I need of the silver nitrate, even though it's in excess. 506,500. Here to here, or here to here. I would need to use that number if I'm jumping from here to here, because that's how much we actually use. Okay, but this is a 1-to-1 ratio, so it's going to be a gaining of 25, 3, 2, 5, 0. And from here to here is again your plus 5, 0, 6, 5, 0, 0. And this is how much we're going to get of each one. All right, another example. 22 grams of propane burns. Calculate the number of moles of oxygen used and produced, and product produced. Fill the tables. Now, one small thing here. This is a sort of a harbinger of things to come here. Really important here. Okay, this number here. Let's balance this quickly here. So try it on your own. So 3, 3, 8, 4, 4, so 6, 10, so I need 5 here. So this 1 and the 5 and the 3 and the 4 represent number of particles. It doesn't represent mass. So my stoich ratio, the only thing I can't use my stoich ratio with, the stuff I just did, it's not a ratio of mass. Not ratio of mass. Means that 1 gram of this doesn't require 5 grams of that. That is a big no. That's really bad. Okay, so we're going to just pretend we never. Well, it doesn't pay to ignore the issue, but because it's definitely a problem. Okay, we cannot use grams in our ice table like this. So let's go ahead and let's see what we do here. Well, I got to get this into something else. Okay, moles. And we did this thing so far in particles. Now let's try this out in moles. Okay, so particles, that's a mole. A mole is a particle. So let's add this thing over. Propane. What do we got here? C3H8. I need to convert this from grams over to moles. Carbon is going to be 12 times 3 is 12.4, 36. Plus another 8 is 44 grams per mole. You'll notice that we have less than 1 mole. In fact, look closely, it looks like we have exactly half a mole. 22 grams. And you know it already. You know it's less than 1. It's close to half. Grams to moles. 1 mole is 44. This math should just convince you of your estimation. Alright, so let's use the 0.5 moles as opposed to the mass. This is now gone. Remember, mass is just a means that we use to count. In fact, I flipped this from grams to moles, but moles to actual number of particles is, on the human terms, isn't something that we do very often. Like I'm never going to use Avogadro's number in a real life situation because people have to work with bigger numbers of particles because the particles are so small. Initial stoich ratio, and I have 0.5 moles of this. I have excess of this. Take a moment to fill the rest of the table out. Pause the video. Alright, 0, 0, minus 0.5 down to 0. Alright, I'm going to jump from here to here at a 1 to 5 ratio. 0.5 and a 1 to 5 ratio is half of 5 is 2.5. So minus 2.5 moles. Jump from here to here. Everything's based off of that limiting for the most part. If it's not based off this, it's based off something that was based off of that. Eventually, everything came off of this 0.5. So I'm going to jump here. 5 moles, 0.5 moles at a 1 to 3 ratio is 1.5 moles. 3 of those. So this is gaining 1.5. And I'm going to jump from here over to here as well. Okay. And that's going to be 0.5 moles at a 1 to 4 ratio, and that is 2 moles. Plus 2 moles. You can confirm the fact that if you were to jump from here to here, you would also get the same. Let's do that. 1.5 moles at a 3 to 4 ratio, and do your math calculator, you'll get 2 moles. Okay? So, with that being said, doesn't matter how, but this number came from here. You would never want to use the excess reactant. Now, you could use the excess reactant, but only if using the actual 2.5. You wouldn't want to use this number. Certainly not the amount left over. Alright, so plenty of good stuff there. Should be starting to feel a little more comfortable with that, and here's another one for you to try. Okay, again I got grams here. We're really trying to emphasize the fact that the mass cannot, absolutely not be used. Mass not used. Let's do this here once. I got, again, we just balanced this thing, so it was a 5 to a 3 to a 4 ratio, I believe. And there it is, okay. And a 1. Now here it says a second experiment finished with 27 grams of water. Okay, let's fill out the ice table here, or how much of the other things am I going to get? So I'm going to do initial, stoich ratio, and let's just kind of see what I got here. 27 grams of water. Get rid of grams and go to moles. 1 mole is 18 grams, and you'll see that, well, 18, well, I messed that up. Alright, it's good because my estimating wasn't working out. 27 grams, get rid of grams and go to moles. 1 mole is 18 grams. And this division divided up, I believe, is 1.5 moles. So I'm getting, in the end, 1.5 moles. And sometimes at this point, you want to know how much, a common question might be, how much propane was used? Okay. So we're going to jump from here to there. And that's fine, you could do that. It would be pretty simple. It would be 1.5 at a 4 to 1 ratio, and 1.5 divided by 4 should be an easy number, I believe. 1.5 divided by 4 equals 0.375. Okay. So in this case, this thing reacted, and I had a certain amount to start with, I lost x of it. I lost 5x of this. I gained 3x, and I gained 4x. And I had none of this to begin with. I guess the question here might be, what's x? 4x. And either way, or you could just make manual calculations, just jumping, using the stoich ratio to all of these guys. Let's do that one. So I just did this one. So this guy here is 0.0375. So this one here is, I started with 0.375 here to here, a 4:5 ratio. Okay, 1.5 at a, get rid of the H2O, we'll go to the O2. I'm going to go from here to here. So I'm working backwards. That's fine. 4 to 5 ratio. So I'm going to get them a little bigger than 1.5. And it's going to be 1.5 times 5 divided by 4 equals 1.87. So this guy is 1.87. You can bet your bottom dollar here that this guy is 5 times that one. Okay, so let's keep moving here. We got 1.87. Keep numbers there. That's a big no-no to do math and not put an answer there, because if you don't put an answer there, that work is useless. 1.5, useless for grading at least, at a 4 to 3 ratio. Drop from here to here. And 1.5, that's going to be, alright, 1.5 times 3 divided by 4 is 1.12. Okay, 1.12. This is how much I get in the end, 1.12. And of course we got our 1.5 here. These are all the values that we're going to get out of this ice table. And again, lots of good stuff here, just looking to bounce around between ratios. Our next example will be a little more investigating of the limiting and excess reactions. Thank you.